Morning friends. Today I will discuss the fast reaction by nuclear magnetic resonance method. I have divided this lecture into two parts. In first part I will discuss some of the fundamentals of the NMR method, and in second part I will explain how a fast reaction successfully studied by NMR spectrometer. Before I start my presentation, I would like to discuss some of the important literature available for the fast reaction. As you know that there are many books available for NMR method, but for this particular lecture I have followed the book that is chemical kinetic methods, because I have already discussed many fast reaction methods like stop flow method, relaxation method, flash photolysis method, femtosecond spectroscopy method, and now I will concentrate only on the NMR method. And in this book of Professor C. Kallol, a very detailed description of NMR method is available. The student can refer this book also. For fundamental aspects of NMR, I have referred spin dynamics, very important books, the basis of nuclear magnetic resonance by Malcolm Levitt. And in addition to that, I have also referred some of the very famous books of spectroscopy. I have also referred the instrumental method of analysis books, etc. Now, what is our objective? Our objective is that how to study a chemical reaction by the NMR method. And if I am talking about the chemical reactions, there are some simple reactions, conventional reactions, and there are some fast reactions. But in this chapter or in this discussion, we are interested in only in the fast reactions. And fortunately, there are many research papers available. Some are very old. You see that Journal of Chemical Education, it is published in 1967, and some are also very new research papers, like studying the fast reaction kinetics with online NMR spectroscopy, because if the half-life is very low, like 10 to the power minus 9 or 10 to the power minus 10, that can also be studied with the help of NMR method. Of course, we have to design as per the requirement of the chemical reactions. And similarly, it is also a very good paper, that fast kinetics studied by the NMR. In my second lecture, I will discuss details of that method. And that is also a very important paper. Time and site resolved kinetic NMR for real-time monitoring of any types of very fast reactions. This paper is also very important, that is rate constant determined by the nuclear magnetic resonance method. Why I am showing all such type of research paper? That because it is a research oriented topic, so you must refer some of the good research papers in order to learn the complete information of that, how the NMR method is useful for studying the fast reaction with the help of chemical shift or spin coupling and other things. Now, before I start the fundamental of NMR, I must tell the student the first Nobel Prize in magnetic resonance or the new methods for nuclear magnetic precision measurements. So we always mention these two great scientists, Professor Bloch and Purcell, because they were won Nobel Prize in Physics in 1952, and fortunately still for studying the NMR method, the magnetization, magnetic moment, rate of change of magnetic moment with respect to time, we have to follow the Bloch equation, and long back in 1946 he has published this paper, and still we are following that process for studying the kinetics of fast reactions and Bloch equations. Similarly, it is also very interesting that student must know this two Nobel Prize in same university. You all know that the very famous university ETH in Zurich, Switzerland, in the same chemistry department, but in 1991 Professor Richard Ernst, a very famous person, is awarded Nobel Prize. First time he actually discovered the high resolution NMR, or that is sometimes the concept of Fourier transform NMR, and of course some contribution regarding this MRI and other things. Similarly, in the same university in 2002, Kurt also awarded Nobel Prize for the study of the NMR and the protein structure. And so there are four scientists, Bloch and Purcell, as well as the Richard Ernst and Kurt. And again, you all know regarding the application of the NMR or the importance of the magnetic resonance imaging, and that two scientists, Professor Mansfield and Professor Lodbar, they also won Nobel Prize for Medicine, of course, 2003, for invention of the magnetic resonance imaging. So this is the brief history of the development of the NMR and the Nobel Prize of the NMR. Now I am coming to actual point, and because I think in B.Sc level also you have studied some fundamental aspects of the NMR. But here actually NMR, we are using the NMR tools for the studying of the fast reactions. So I must say that you might have heard all the spectroscopic technique, but NMR spectroscopy is one of the most important and widely used analytical techniques. So many biological reactions, biological applications can be studied with the help of this NMR spectroscopy. And if you ask me, so what is the actual definition of the NMR, I must say it is a radio frequency spectroscopy where electromagnetic radiation, that is basically, I'll explain, the radio wave frequency is absorbed by molecules. Of course, that molecule must possess non-zero speed, that means that type of nuclei must have a particular nuclear spin. Of course, that is I. That molecules or the nuclei must be NMR active. So in one sentence, you can call that absorption of electromagnetic radiation in the radio frequency region. That is actually NMR. That is, when we placed such type of NMR active nuclei in the external magnetic field, then of course how we study the NMR signal. So if you see the electromagnetic radiations, whole range, particularly the radio frequency range it is 3 kilohertz to 300 gigahertz. And of course, if you consider only the typical frequency, that is up to 10 to the power 8 hertz, and typical wavelength is 3 meters. So you know that in periodic tables there are a large number of nuclei, but I have given some of the most important NMR active nuclei, and if you read it and if you see why such type of nuclei are NMR active, there is certain condition, and that condition is that if you see all those nuclei, the mass number is odd, as that means the number of protons and number of neutrons is odd, and atomic number is odd or even. That type of nuclei shows some spin. Of course, nuclei with spin have some angular momentum, and if you see very carefully, like carbon 13 or hydrogen or nitrogen 15, and if you calculate the spin quantum number, so either there is a half integer spin and integer spin, and of course there are so many other concepts that the natural abundance and other things, they are magnetic moment, but you just consider that such type of NMR active nuclei must show spin quantum number half, 3 by 2, 5 by 2, 7 by 2, 9 by 2, or even some integer spin like 1, 2, 3. And most of the biological system, you know that such type of elements are very important, like phosphorus, sodium, very important things are there. So therefore, of course, we can select the nucleus in the software and adjust the probe for such type of the operation. So that is the most fundamental point of this. So first thing is that such type of NMR active nuclei must be taken, but most commonly used nuclei is carbon 13 or hydrogen, nitrogen 15 NMR and other things. For some biological studies we are using other type of nuclei also. Now, a very simple thing that when in NMR spectroscopy, when a sample is exposed to an external magnetic field, so the nuclei, of course, depending upon the types of the nuclei, definitely they are having different magnetic moments. There is a flipping and they are excited, and there is excitation from low energy to the higher energy, and then it emits the resonance frequency, and that resonance frequencies are recorded, converted and analyzed. Now what happened after absorbing a characteristic radio frequency, the excited state nuclei return to the lower energy state by transferring energy to the surrounding environment. That is the most important part for the chemical kinetics. because you apply the magnetic field, there is a flipping. I'll explain the diagram, and it matches with that radio frequency, the energy difference, and then there is a transfer from higher energy level to the lower energy level. Now that is the most important part for studying the chemical kinetics. Now there are two types of the process. One, that energy is transferred to other atoms or the solvent or the surrounding environment. That type of relaxation process is called spin lattice relaxation. And other system is that, if of course that is sometimes it is called the longitudinal relaxation, and there is another type of relaxation that is called the transverse relaxation. In that case, energy is transferred to the neighboring nuclei, spin to spin, at the same energy level, and that is also referred the spin-spin relaxation. When I will discuss the kinetics, fast reaction kinetics, then I will completely explain the role of spin-spin relaxation. And these two relaxation processes are characterized by time constants. So we have to measure the spin lattice relaxation time and spin-spin relaxation time. And that spin-spin relaxation time are responsible for the resulting NMR spectrum. And that particular decay, that means from higher energy level to lower energy level, is the time constant for decay or dephasing of the transfer magnetization. And that can be monitored. So the rate of change of magnetization or magnetic moment with respect to time can also be calculated, and this is, as I told you, that this is a longitudinal direction, and therefore it is called the longitudinal relaxation, and of course restoration of the Boltzmann distributions. This is the external magnetic field, and this is called the decay in the transverse components with XY plane, and that is the most important part for the chemical kinetics. While discussing the kinetics, I will explain the role of T1 and T2. Now, why it is called actually resonance? Why it is called the nuclear magnetic resonance? Because when we apply this external magnetic field, that field forces the nucleus to spin a particular direction, maybe in the direction of the external magnetic field or the opposite direction. So by providing just the right amount of the energy, the spinning nucleus can be forced to spin in the opposite direction. So this is resonance, and the nuclei now has a magnetic field direction that is against the applied magnetic field. So that is very important, the resonance behavior and the flipping of that plus half and minus half, like that. So you all know that if this nuclear active or NMR active nuclei, so there is a precessional movement when there is a magnetic field. And now you can understand this thing, that this is the actually flipping, spin flip. So that is actually higher energy level, and that is the lower energy level, and you can very easily understand that type of is anti-parallel spin. It is parallel spin, and yes, there is particular type of energy. You can write it as alpha or it is beta, and so delta E can also be calculated with the help of. When there is no field, no external magnetic field, there is no change. But when we increase the external magnetic field, so the energy difference depends upon the, or you can call it directly proportional to the external magnetic field, and that is also directly proportional to that radio frequency. So therefore it matches with that radio frequency. Then of course it releases the energy, and when it releases the energy, that process is called the relaxation process, and spin relaxation and spin lattice relaxation. So magnetic nuclei are in resonance with the external magnetic field if they absorb energy and spin flip from low energy level to high energy level. That is the explanation. You can understand these things. Same thing I have written just otherwise. And as I have already told you a few minutes ago, that the frequency of the electromagnetic radiation is proportional to the energy difference between these two states, and that is also proportional to the magnetic field. That means if I increase the magnetic field, maybe it may be increased like that. If it is magnetic field is so this delta is low, then delta E like that. So it is directly proportional to the external magnetic field, and accordingly it matches this radio frequency region. And now I must tell you that basically there are two types of NMR machine. Long back people are using the continuous wave NMR. Now we are not using that continuous wave NMR. And the continuous wave NMR means, that means 90 megahertz machine, that the magnetic field is fixed and we change the radio frequency, or vice versa. Radio frequency is fixed and we apply the magnetic field. So it is a very old system. So fixed magnetic field and sweeping of radio frequency by varying the current in a frequency coil to get the resonance absorption signals. But after the discovery of that Fourier transform NMR, of course by Richard Ernst, now the system has been changed, and most of the present NMR machines are called the Fourier transform NMR. Here you see that time domain is converted into frequency domain. The nuclei in the magnetic field are exposed to a short duration, 10 microseconds, pulses of radio frequency radiation. And then of course there is a relaxation, and the relaxation is referred as free induction decay. Again, that is T1 and T2 based on these things. Now the last part of this, because this first part is a fundamental of the NMR. Fundamental of the NMR. I will not discuss what is chemical shift and other things. My objective is that how NMR will be helpful for studying any fast reaction. Therefore, I am just using this type of NMR. And it is only for the preliminary students who are not aware of the NMR. Now, fortunately, in our university, we are having a very good NMR machine, 400 megahertz. So I have taken these photographs to National Center for Natural Resource of our university, Pandit Ravi Shankar Shukla University, and I am really grateful to Professor M.K. Dev and his student Dr. Ram Singh Kurre for giving me all the information about this NMR machine. Actually, you see that there are three parts. One, you all know that magnet and probe and other things. Of course, it is a superconducting magnet. very good. And another part is probe. I have not shown you the probe. And the heart of that NMR machine is called the console. You see, console. Console, you can call it is a control unit, and it communicates with NMR probes, or you can call it, the role of that console is the generation of pulse sequences and acquisition of data, manipulation and other things. And now everything is controlled by that computer. So now if I see the block diagram, and this diagram is available in the most of the undergraduate or postgraduate books, the schematic diagram of the NMR machine. So naturally there must be some magnet, high speed superconducting magnet, and this is actually NMR tube or the probe, and there are of course two parts. One is the radio frequency transmitter, another is the radio frequency receiver, and that of course it is linked to the control console and computer. Now what is the important point is that for maintaining the superconducting magnet, there must be some cooling system, and because it is low temperature superconducting magnet. So now we have performed some of the experiment, and you know that this is actually Dr. Ram Singh Kurre, and very recently I have taken these photographs. So it is the whole chamber magnet and probe and other things. I will explain the role of liquid nitrogen as well as the liquid hydrogen, a console. This is just how we take the NMR spectrum, or like that. So there is a most important thing is that we have to put the sample in a NMR tube, and it goes to that probe. So you see, this is the NMR tube. It's a very small type of the NMR tube, and we must pour this NMR tube in this probe, and it will reach in this system. If you see very carefully, there are two tanks. It is written here, you see, nitrogen fill in port, nitrogen fill in port. Another is, you see, helium fill in port. Because you know that it is a superconductivity magnet, so the magnetic coil, I am not discussing the details of the magnetic coil and other things, but this magnetic coil is immersed in a liquid helium tank to maintain the low temperature, like 4K or 2K, like that. Because if we maintain the low temperature, then of course it also maintains the superconductivity. And in order to cool that liquid helium, every week we have to pour this liquid nitrogen, and we are arranging liquid nitrogen from Bhilai steel plant. Every week we use that cryocan, and we bring this liquid nitrogen for this thing. So one objective of that liquid helium for maintaining the low temperature and the superconductivity, and liquid nitrogen is used to regularly minimize the heat into the helium tank, so that there will be minimum evaporation of the liquid helium. So that is one of the maintenance part of that NMR machine. So here it is nitrogen filled port, and it is nitrogen and it is liquid helium. There are two, there is a tank, helium tank and nitrogen tank. Now again, if I see the block diagram, it is just a close-up of these things, helium filled in port and nitrogen filled in port, like that. Now if I just for the student purpose, they can understand this simple diagram, they can understand the most important part is that probe is very important. There is a magnet and other things, and it is a vacuum chamber, so it is like nitrogen tank, it is helium tank, and this is actually probe. This is sample in NMR tube, because we pour in this side, so it will, with the help of air pressure, it just goes to this thing. And the probe is very, very important. We can control everything with the help of the probe. So it actually transmits the radio frequency pulses. And there are two parts. One is radio frequency receiver and another is the radio frequency transmission. So transmitting radio frequency pulse and detecting that when there is a relaxation process, and from higher energy level to lower energy level, it releases that radio frequency signal, and then that is converted into recording coil and it is converted into product and like that. So this is very simple formation of a NMR machine, and ultimately when we understand these fundamental points, then we start to study the kinetics, and we are getting, suppose I am studying the exchange reaction, like if I take dimethyl acetamide, so what about whether there is a fast exchange or slow exchange? There is no exchange. That means before exchange, what types of signal we are getting, what type of peaks we are getting. So I am just showing one example. Here I am just showing this thing, that this is in my next lecture I will explain this kinetics. So NMR determination of the rotational barrier N dimethyl acetamide. There are two methyl groups. Suppose this is A and this is B. So after exchange, you see the isomerization type of this cis trans isomerization reactions. And when we see the NMR spectra, we are getting different types of peak. So how we interpret or how we study such type of fast reaction with the help of the NMR? What is the reason for that? Why such type of peaks? What about the radio frequency changes? Why there is a flat? Here it is very clear cut. Two signals are shown. So let me conclude that in the first part of this lecture, today I have explained the very fundamental of the NMR spectrometer and a general discussion of the different parts of the NMR machine and what is NMR active nuclei, what is the role of external magnetic field and radio frequency region, why it is called the resonance. And in my second part, which is the actual course content of this course, your M.Sc second semester course, that how there are so many fast reactions, but I will use one or two reactions, and how this rate of the reactions or this cis trans isomerization can be studied with the help of NMR spectrometer. So that is the main purpose of this course. Thank you very much.